Hi, well, I'm Stephen Neshaba, and I'm here to give you some pointers on the understanding transition metal cation complexes. So the one I just want to focus on today is our complexes of the chromium 3 plus ion, which I'm going to write like this. It's chromium 3 plus with the 6 ligands around it. The ligands are going to be either ammonia or water. They're going to be acting as Lewis bases, the ligands, and the chromium is the Lewis acid. And the geometry of this is an octahedral configuration where you have those six ligands around in that configuration. So just focusing first on the molecular orbitals of the chromium, or the atomic orbitals of the chromium, we just imagine there's a whole bunch of orbitals and they've got electrons in them and so forth, but the highest lying orbitals are the d orbitals of the chromium, and since it's chromium 3 plus, there are 3 d orbitals. So 1, 2, 3, 4, 5, those are the 5 d orbitals and the 3 electrons in them. Now, those orbitals on the chromium are going to interact with the orbitals on the ligands. Now, so, here's, for example, an orbital on the ligand, okay, and here's another possible orbital on the ligand. And here's a couple of d orbitals on the chromium. That's the chromium there, and I've indicated them with nodes. That is to say, there'd be a red-blue color change, a phase change, indicating antibonding interactions. And the idea here is that as in any Lewis acid-base reaction, the orbitals on the Lewis base, which I've indicated here, 6 of them. Those will be stabilized by their interaction with the Lewis acid, but then there's orbitals on the Lewis acid that will be destabilized. So here are the 6 orbitals on the Lewis base, stabilized. They started off each with a pair of electrons in them, just because there's that pair of electrons, and there are 6 of them. And I've drawn the 6 down here. Now for the Lewis acid, the chromium, there are those 5 d orbitals again, and I've drawn them as being destabilized. So a key idea here is that not all 5 of those d orbitals are destabilized to the same amount, and the typical pattern for an octahedral geometry is that 3 will be destabilized by either not at all, in which case we call them non-bonding. Those would be drawn a little bit lower than I put them, or pi star, which is destabilized a bit, and then the most destabilized we're calling the sigma star, and because of this, we get this, split, and we can't lose any electrons here. So, sure, there's lots more electrons in the molecule, the complex as a whole, but in particular, those 3 electrons that were on the bare chromium in the d orbitals stay in these destabilized d orbitals. There they are, one thought about that is. Let's just think about what they might be if they were sigma star. I've kind of drawn a sigma antibonding interaction between the ligand and the metal d orbital. That's because, well, it's antibonding because of the sign change, but it's sigma because if you kind of look down that axis, it would look symmetrical about that axis. And here we have a pi star antibonding orbital. This one here is sigma star. That's a pi star antibonding orbital. And so those appear here and here. And the only final thing just to mention about this is that this has everything to do with why transition metal ion complexes are colored, and it's because there's this split right here, which gets a special name, delta naught. If a photon comes in and it's got just the right energy that matches that energy gap, then an electron gets promoted from there to there, okay, and it absorbs that photon. And if that energy gap, which is called the crystal field splitting, if that energy gap lies in the visible range, then the substance will be colored. Okay.